Everywhere you look in nature, you'll probably find some sort of spiral pattern somewhere. From cyclones to fern frogs to seashells, nature is filled with beautiful spiral patterns. But this makes you think, why is that? What makes this pattern so prevalent and abundant in the natural world? You may have heard that all of this is connected to the golden spiral, a sacred curve that has proportions based on the golden ratio, or 1 plus root 5 over 2, and apparently appears all the time in human art. Surely it would make sense that all spirals that we see are based off this mystical spiral, right? So today, we'll be looking at the Nautilus shell spiral, one of the spirals that is most commonly compared to the golden spiral. It's also both coplanar and a definitive spiral shape, so let's put this math mysticism up to test. First, I graphed about 10 points on the spiral based on its theta and its radius, from 0 to 11 pi over 2. Clearly, the growth in radius is not linear, and by graphing the theta versus the radius shows a logarithmic growth pattern. As it turns out, the shape of the Nautilus shell is a logarithmic spiral, a graph that has the general equation r equals a times e to the power of b times theta. The a determines the original radius, which in this case is 1, and b determines how tightly the spiral winds. This specific Nautilus shell has a b value of about 0.172, which is pretty close to other values I found online. Another name for the logarithmic spiral is the equiangular spiral, and this is because if you draw a line from any point in the spiral to the origin and draw a tangent line to that point, the angle between the two lines will be the same at any point on the spiral. If we use the general position function, we can make a coordinate vector, then find the derivative of the function to give us the vector tangent to the point. Using these two vectors, we can solve for the angle between the two vectors to find that it always equals b over root 1 plus b squared, which stays constant throughout the entire spiral. This means that the spiral will not change its shape no matter how much you zoom in or out. It's self-similar. So what does this actually do for the Nautilus? First of all nautili live in a very wide depth range in the water, from 5 meters to as deep as 700 meters. They have a tube that connects all the chambers in their shells called a siphuncle, and they can fill the chambers with fluid and change the density of the fluid to help control the Nautilus's buoyancy. The Nautilus only really inhabits the outermost chamber, meaning all of its inner organs are in the outermost chamber, and the shape of the spiral allows it to grow outwards from the spiral without changing the shape of its shell. As it grows, it moves its internal organs to the next chamber, and the previous ones are now used to control its buoyancy. As you can see, zooming out of the spiral causes it to have the same shape as before. So let's go back to the question of whether this spiral is the same as the golden spiral. A quick Google search shows that while the golden spiral is also a logarithmic spiral, its graph has a b value of about 0.30635. It's safe to say that the Nautilus shell is not the same spiral graph as the golden spiral. So does this mean that the golden spiral's prevalence in nature is overstated? Mostly. But there's one place where it has a practical application. So it's somewhat well known that if you count the number of spirals in pine cones, succulents, and flowers, you'll get a Fibonacci number. The Fibonacci sequence is the chain of numbers that you get from adding the previous two numbers together, starting with a 0 and 1. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. So in this pine cone, we see 8 spirals, and no matter how you count the spirals on the sunflower, the number of spirals that you get will always be a number on the Fibonacci sequence, 21, 55, and 34. This can be explained by the fact that the angle that plants put out leaves and seeds is the golden angle. The golden angle is measured to be about 360 degrees divided by the golden ratio squared to get a value of about 137.5 degrees. It turns out that the ratio between the consecutive numbers in the Fibonacci sequence approaches the golden ratio, causing the number of spirals to be Fibonacci numbers. This angle is useful for leaves because if plants put out leaves at this angle, it takes a very long time for the plant to eventually cover one leaf with another, since they don't overlap. In 1979, a mathematician named Helmut Vogel used this angle to create a very accurate model of a sunflower center. He used a polar graph called the Fermat's spiral, a general equation r equals positive or negative a times the root of the angle. A graph where the spiral is initially sparse but winds closer and closer together. In the model, a computer program put out a seed at every rotation of the golden angle, and what he got was a very densely packed pattern, but with no overlap between seeds. This angle is very important because just shifting the angle slightly caused a completely different pattern to appear. A unique property of Fermat's spiral is that the area of all its annuli, the ring in the spiral, are all the same. The white, blue, and yellow regions shown in the graph all have the same area. So why does this matter to the sunflower? By putting out the seeds in the angle and in the pattern described earlier, the sunflower can give each of its seeds space from other seeds while also being very space efficient. Therefore, it can produce a large number of healthy seeds. Furthermore, the equal area of each annuli in the spiral shape allows it to divide the seeds evenly in each spiral, so it's easier for the sunflower to keep the same number of seeds and distance between each seed in every ring. Once again, nature has shown us that it knows what it's doing. While it may not all be as meaningful as the golden spiral, animals, plants, and other organisms use the math that works for them and their environments. Thank you for joining me on this journey in learning about the spiral graphs found in the world around us.